Hello, my name is Rolando Chacon. I am Associate Professor in Steel Structures.
Hello, my name is Carol Puig and I'm Associate Professor of Geomatics Engineering.
Hello, my name is Esther. I'm full professor of steel structures, and we are members of the Department of Civil and Environmental Engineering at the UPC in Barcelona.
This presentation is about the use of systems for tests on stainless steel members and frames aimed at interoperability. This investigation belongs to a vaster project on structural behavior of stainless steel frames subjected to static and accidental loading. This is a national project that has already ended and in which different types of structural tests of austenitic stainless steel elements were performed. For instance, we performed tests on tensile members, also tests on rectangular hollow sections using different cross-sectional classification, material tests on cyclic loading, in which cyclic hardening was studied, members, columns and beams with different cross-sectional classification subjected to compression and bending, frames subjected to horizontal and vertical loading. This was one of the most ambitious tests performed in steel structures at our lab facilities, in which the test configuration included the application of load vertically using jacks, but also the application of horizontal loads on the base of that frame using horizontal jacks. This also allowed to perform cyclic loading testing, in which horizontal cyclic load was applied, as you can see in the video. And two types of instrumentation were applied: traditional, using traditional data loggers, and alternative, using microcontrollers and microcomputers. This was fundamental for the development of alternative IoT platforms, LiDAR systems, virtual reality and augmented reality systems for laboratory facilities, with an open, interoperable, beam-enabled philosophy, accessible also to a broader audience. So let's describe these systems. The first case is the IoT platform for lab facilities. Using members and frames, we instrumented the beams, the columns, and the frames with displacement sensors, lasers, and ultrasonic in order to measure deflection, out of plane displacement, and in plane displacement of the frame. These measurements were sent to a developed platform, IoT, called Camin Smart Lab, which is now available at our school for any researcher or student, in which with a sensor they can connect this experiment to this cloud-based platform for researchers and students, and they can allocate all necessary files and measurements in real time. It uses an interoperable format compatible with open source systems. And the second part corresponds to the terrestrial laser scanner, scan to beam. The use of a TLS during the test on the stainless steel frames was aimed at measuring displacements prior and during testing. Okay, so automatic usage of these results as built input in geometrically nonlinear analysis was the aim. Here we can see the frame being tested and the terrestrial laser scanner scanning the structure and given a number of points. So a cloud of thousands of points was exported to post-process, Rhino, Grasshopper, and Python were used for post-processing techniques, in which computational geometry was used to treat this information using Python developed in-house coding, in which we identified these surfaces, these clouds, and transformed those clouds into lines that were used subsequently in models, which are the models we understand for geometrically nonlinear analysis, in which beam elements are used, and structural analysis is then performed on such type of reproductions. Here you can see the model already under loading. Different visualization of results in real time as well. The third part is the development of virtual and augmented reality systems on the test on those frames and members. The aim was to develop a real-time enriched visualization of the test for two types of users: remote user and a user at the lab. Virtual reality for the former, augmented reality for the latter. The system proved useful for three different collectives at the research group: researchers, technicians, and students. Also using interoperable format compatible with open source measurement systems, microcontrollers, in which structural models were solved in real time using different computing platforms. Let's have a look on the virtual reality, which is a synthetic reproduction of the lab. We need for that a helmet in which an immersive synthetic environment is reproduced. This is a reproduction of the laboratory facilities and also real-time data processing from those sensors, giving information to the model, and the user could see in real time the deflection of the beams and the deflection of the columns, in this case out of plane displacement. This was an immersive synthetic environment. On the other hand, the augmented reality, which is an enrichment of the naked eye vision during the test, using measurements and using glasses, HoloLens, that's the name of those glasses in this case, in which with these glasses the user can see the real laboratory, but on top of the real laboratory there is a layer of information that provides graphs, plots, lines, numbers, arrows about bending moment, axial forces, displacements, reactions, and meaningful information in real time. This information is directly linked to the model that is calculated in real time with the sensor information. So let's have a look at the key takeaways of what we have done concerning interoperability in three different lines. First, sensor to cloud using interoperable format, JSON XML. Second, scan to beam using computational geometry for treating this information of a point cloud. And third, sensor to analysis using different user interfaces in real time, such as VR, AR. So one can see in these three lines a left to right, let's say, transmission of information. Sensor to cloud, sensor to beam, sensor to analysis. But this is important, this is possible, this has been performed here. But also one of the things that is a key takeaway is that the flow of information can also be not only horizontal but also vertical. When I mean vertical, is that the information can also go from the cloud to the beam, from the cloud to the analysis, from the beam to the user interfaces, and vice versa. And all of this is meaningful when it comes to the new trends in construction. These new trends in construction are going beyond BIM, and this is a need in practical construction 4.0. in which beam plus time plus sensors is generating the so-called digital twin of the structure, which is a new concept, or relatively new concept, in which measurements, sensors, images, analysis, interfaces, cloud services all together are enabling the development of this concept of digital twin in the realm of steel or in general structures. We need to use this digital twin concept for taking decisions, and so we need useful and practical ways of representing these decisions for engineers. That's a new challenge. But interoperability wise, we see this as what the islands we knew before, in which all islands were well developed. Now in this island of information, we can put information flowing from one island to another. Finally, we would like to point out some references about this work we have already published in journals, and we would like to acknowledge to the great team working hard in this development of this experimental program, together with the collaborators that help developing specific tools for this task, and the funding agencies for the project Pinox stainless steel frames subjected to static and accidental loading. We look forward to hearing from you.